Good?
Yep.
Okay. Today we're going to talk about rheometry, or another word for it would be rheology. Do you know?
Study of fluidity.
Study of fluidity. Yeah, rheo means stream or flow. And then logy means study of, where metry means measure. So what we're doing is we're looking at the flow and deformation of, usually we're talking liquids, but there's sort of this weird middle ground between liquids and solids of like gels and pastes. So rheology applies to those as well. And the main things that we're going to study is going to be stress, strain, and shear. Those are going to be our main, like our big words as we're working here.
And shear rate.
Yes, and rate relates to all of these, how fast you're going. You could do strain rate also on this. There are two main rheological properties, and we can sort of create like a spectrum. We have viscosity on the one side, and this is just going to be, do you know the definition for viscosity?
The more viscous it is, the more it resists movement.
Exactly.
Higher strain rate.
So viscosity is resistance to flow. Yeah, so I think of viscosity as like thickness of a liquid. So a more viscous thing is going to resist flow, it's going to be thicker. But if something has viscous properties, it flows. On the other side, we have elasticity. What is elasticity?
How much material returns after you put strain into it?
Yeah, exactly. It is energy retention and then release. And elasticity has 100%, it holds the energy and then it releases the energy 100%. There's no like dissipation of energy. Where in viscosity, if I put, my hand through water, the water doesn't push back on me necessarily. There isn't like an elastic response. That's a viscous response. In between those two is our area of interest for most rheological studies and is viscoelastic. Viscoelastic properties, or the way I've written it, viscoelasticity, which is a material or the property of a material where it both dissipates and returns some of the energy.
Is the audio on?
Yes. I've been checking every time since I had that one failed video. So some of the energy is dissipated, and that's its viscous property, and some is returned, and that's its elastic properties. So let's talk about the way we kind of, we try to turn these into properties that we can experience on a macroscopic level, because it's a little bit hard to imagine these properties when they're mixed all together. So let's talk first about elasticity. let's say I've got a spring, and I'm going to draw springs as zigzags because that is easier for me. The spring has some starting length, right? If I take that same spring, oh wait, I don't want to. And I add a weight to it, the spring is going to extend by some distance. And so we would call this distance the strain. That's the deformation, right? And then, let's see, that was 3. If I take that same material, or that same weight, and I add a second, so here I've got, let's see, then I get double the strain, essentially. And we write the equation for elasticity as a linear relationship. Stress, which is those weights there, is some slope times the strain. So as I add one stress, I get an equivalent amount of whatever this strain is out of the system.
It is, but it's Hooke's law, but expanded.
I could not tell you. I don't know Hooke's law.
It's essentially the same exact equation, but meant for springs.
Oh, right, cool. And in this example here, we're talking virtual elasticity, or like perfect elasticity, where there's no amount of stress that I could put on this spring that would break the spring. So we're assuming forever and ever, if I add 1 unit of stress, I get 1 unit of strain. If I add 2 units, oh my goodness. If I add 2 units of stress, I get these 2 units of strain. Do you know what we call E?
Elastic modulus, or Young's modulus.
Yep. And when we're talking mechanical testing, we use the elastic modulus quite a bit to tell us information about like the strength of the material in its elastic phase, because those are not ideal materials and do eventually break. The elastic modulus relates how much force or stress gives how much displacement or strain. So it relates how the quantity of force and how much displacement that's going to give us. Now let's swap over to the other side of things and let's talk about viscosity. Someone's getting a lot of emails right this second.
Indeed.
So viscosity, we use something called a dash pot. Do you know what a dash pot is?
No.
Cool. It is, have you seen those really satisfying videos of someone who has like, has done some metalworking, and they've got a hole, and then they've got a perfectly fitting like cap on it, and they put the solid material into the hole, and it really slowly lowers down into the hole because it's such a perfect tight fit that the air underneath it creates this cushion, And the thing sliding down has to really slowly go in, and then once it sits, it's like perfect. So that's a dash pot.
Neat.
A dash pot is some sort of very well-fitting cylinder or, shape inside of a fluid-filled other thing. So here I'm going to draw cylinders. So imagine you've got a cylindrical hole, and then you've got this perfectly fitting dash pot. And if there is liquid underneath, depending on the flow of the liquid is going to have to kind of escape up above the top of the item as I push down on it. And I can put a lot of force into this, but it's just going to move slowly. No matter what, it is going to take the flow of this liquid or of this fluid, like air does this, around the sides of the thing. And so it's going to resist flow. Going back to our definition, resistance to flow. In this case, it is resistance to this downward movement. And with viscosity, I am putting a stress along the top, so I can use the same notation, stress equals, and I have I believe that's nu, sort of the weird Greek N.
Yeah.
And then the speed at which we are moving downward, we use this symbol right here. We call this shear rate. Do you know why we call it shear rate? It does have a little dot on top, by the way. It's the upside down fish with the dot on the top. I am confident it has a name.
It is, shear rate is how, because eventually you're going to get more and more shear, and so you're seeing how fast is that shear, how fast is it increasing?
Yes. In the dashpot example, what is shearing?
How much fluid comes out?
Yep, it's this fluid right here that is shearing. Shearing means it's moving kind of past a more stationary object. So in this case, this piece right here isn't moving as fast, and this fluid has to move quickly past it. So the shear is happening at this surface. And shear rate matters because this is a time relational question, where above, elasticity, we have almost an immediate reaction. I put a strain on and the spring deforms. Here, I put a stress on and then I have to wait for all of this liquid to get out of the way. So the shear rate, which includes sort of this time component, is important to us.
Hydraulic go burr.
Yes. This nu is viscosity. And again, that is viscosity of the fluid. And just like the elastic modulus above, viscosity is used to relate force, which in this case I've drawn as stress, with displacement, which is shear rate. So you can see we have two almost equivalent equations. I've got this one right here where I have stress equals some modifier times displacement information. And here I have force information and a linear modifier and a displacement information. So combining both models is viscoelasticity. So we'll go back to black. And if we're going to continue with the metaphor, there's a bunch of different ways we can combine these. So I could have a spring attached to a dash pot. in this case, if I put a stress downward, I would have immediate deformation, right?
Mhm.
And I would also have slow, I'd have a slow relaxation or flow. Because this spring would be the intermediary to kind of carry the extra force for a second. And then eventually the dash pot would allow that force to release, and the spring would return back to its starting displacement. We also, let me move that down because I got that way too close to those words. Arrow not coming with, that was rough. Okay. So that would be in series there. We also can draw it in parallel. This one, if I apply stress, it's going to do slow deformation because this dash pot is going to slow down the process of things. So the important thing here though is like not everything is going to fit cleanly into this or this model. We're going to have variations from material to material, and maybe it's some weird combination of these two things where I'd have to draw this really big, complicated spring and dash pot model in order to model it. So, kind of putting all of the models aside, because none of them are going to really explain what we're doing.
And then there's beam fluids, which is...
Well, and so that's what I'm saying is like, we've got more and more complicated things that we can stick stuff on. The important principles of combining the viscosity and the elastic properties is that something is going to have a combination of a spring response and a dash pot response. Springs, if something is more spring-like or it has a higher elastic response, it is infinitely elastic. It does not deform, not plastically. It is an immediate stress response. And it has a full return of energy. That relates to that infinitely elastic thing. Where on the other side, the dash pot or viscous response reacts slowly to stress. It reacts steadily. That's that time component in the strain rate. It's going to react at a constant kind of speed of deformation. And it will never bounce back. Often it's also infinite. Obviously, in this example that I've drawn, it will eventually hit the bottom of the container and not flow anymore. When we're talking about a material's viscous response, often that is also infinite. So, One of the most common tools for measuring rheological properties is a rotational rheometer. There are ways to measure just viscosity, and that would be for materials that fit really nicely in just this viscous response kind of column category. But for materials that have a little bit of elastic response and a little bit of viscous response, a rotational rheometer is the best. And to give our brains something to like grab onto, this would be something like a hand cream or toothpaste, where if you plop your toothpaste out and you like plop it onto the counter, or you put a little dollop of lotion onto the counter, you can see it jiggle. That jiggle is the elastic response. It's deforming and then returning back to its original state without any final deformation. But if I put my finger on top of that toothpaste or that hand cream and I smear it, it will deform. And that is this viscous response. So hand cream, paint has it as well, this viscoelastic property. Ketchup, mustard, basically anything in a squeeze bottle.
Except for honey. Honey is a fluid.
Honey is pretty solidly just viscous. It doesn't, there's a little bit of debate about whether it has any elastic properties or not, but generally it displays mostly just viscous properties. And you're right, honey is in a squeeze bottle often. But that's why it's an annoying squeeze bottle, is because it has none of this elastic response. It's just viscous.
Keeps on coming out.
Just goes forever. All right, so let's draw our rotational rheometer. I have some ranch in a squeeze bottle at my house right now that it just keeps going. It does not have a stop button to it. Ours is a TA Instruments DHR20. So what I'm drawing, the like specific pieces of it is specific to our instrument. There are other instruments that are similar, but there are other instruments that are different. So just as a warning. We have this big long column. And at the bottom of the column, I have some sort of plate system. On the bottom, I have another. This one is stationary. I'm going to put a little X at the bottom. The bottom one stays completely stationary.
I'm assuming it does have a force gauge in it.
On the top.
Oh, that's on the top? Neat.
Ours is. Ours has a motor that drives it around rotationally, hence the name, rotational rheometer. And it has this sort of like disc on it. Color that in to make it look vaguely three-dimensional.
I'm doing much better.
Like I'm doing my best, but we are in 2 dimensions here. And this little disc is a position reader. So it actually optically reads rotational position. And then the motor obviously applies some sort of force. Typically we measure this in torque. And with this, let me double check my colors coming back to, I can do just plain viscosity with a rotational rheometer. When I'm doing a viscosity only measurement on this kind of tool, I'm typically looking at that resistance to flow. And I'm looking at it with respect to temperature, I might be looking at speed of rotation, which is related to that shear rate. I might be looking at torque, which is related to that stress value that we talked about earlier. Those are going to be the main things that I'd study with viscosity. And that would be just like, I want to see how my oil flows. I would put my sample in here between the two plates. I don't know why, but I probably shouldn't make it like zigzaggy because this is a liquid, so it fills really nicely. And it fills all in between those, and that motor is going to rotate, and we're going to measure the resistance to rotation, really simply, and I can change.
At the sides.
And depending on how close together these are, we call this right here the gap. Depending on how close together those are, your material might fall out the sides, which means you need a smaller gap. But ideally we have enough like surface tension and capillary action kind of situation going on where your liquid just sort of like stays stuck between the two plates. We can also, and I'm realizing I did purple and green, and that's really terrible to try to combine. We're gonna call blue, we're gonna do like a kind of medium blue here. That will be our viscoelastic property. Green and purple have that in common. They both use a blue, so that's gonna be why the colors make sense. So for viscoelastic properties, which like I mentioned is more what you're gonna study on a rotational rheometer, we are going to study G prime, which is we call it the storage modulus. Basically, that is the elastic behavior. We're going to study G double prime, which we call our loss modulus. That's essentially our viscous behavior. We're going to study something called tan delta. Tan delta is a ratio of G double prime and G prime. It's essentially our relative degree of energy loss. So that's related, we're relating how much viscous versus how much elastic behavior is happening in our material. And we're going to do all of these just like above. I can do all of these as a function of shear rate, force or stress, time, temperature, and frequency. So those are the potential variables that I can study while I'm looking at these viscoelastic properties here. In my experience, temperature is one of the most common. Frequency is also up there. I think time is a really cool one, but not every material has a time component, so here we are. So those are, let's see, back to 100%, there we go. Those are the kinds of tests or things that we're trying to study with a rotational rheometer. So if these are your questions, then a rotational rheometer is a really great tool for you. Let's zoom in a little bit to figure out how some of these are calculated. When I am working with my material, at this point, we're going to assume a flat plate on top and bottom. And I have my material in between these two plates. And these plates are discs which means the space between those two discs is a cylinder. Yeah? And because the bottom is stationary, it's not going to move. But the top is going to rotate. So if we're looking at just one tiny little section, the top is going to move this way while the bottom stays stationary. This creates this sort of spectrum of forces that different layers of the material are experiencing. So the top layer is experiencing a lot of force. The bottom layer is experiencing no force. And we end up with this almost like linear, where the next layer after the top is experiencing a little less force, and the layer under that is experiencing a little smaller force, and smaller until you get to the bottom where it's not being kind of moved at all. Good. And that creates, I'm going to do my very darndest to draw this. I drew it once in a different app, and which means that I have the capability to do it. And I don't know if that means that I can physically do it right this second, but we're going to try, like I said, our darndest. So we have, it's too steep. I don't find that this note-taking app is the best at drawing shapes. We're doing our best. Okay, so this is essentially what I drew just a second ago in my two-dimensional section here. But now you can see that this top part has moved and the bottom part has not moved. So I have this same drawing as I did before. It's just that one is showing the actual displacement and one is not. Oh no. Erase just the arrow. There we go. And I'm going to attempt now to draw this in a second dimension. I suppose this is technically a third dimension. Straight-ish line. Oh, yes. Killing it.
Mine looks lumpy.
You know what? I have the benefit of a grid here. I don't have any smoothing. I wish this software would provide that a little bit more nicely, but here we are. So we've got the front. I've taken this and I've turned it into a three-dimensional kind of model here. And I could, if I wanted to, draw the additional, like, boop, boop. I'm going to draw the back axis of this as well so that you can see my dimensionality here. All right. I have some force being applied. And that force is being applied right here. I have some displacement from its original position. We call this delta x, which is like I applied some starting force and I got some starting displacement. And you can see that my delta x does diminish as I go down. Yeah? I also have the cross-sectional area along the top of my material here. And I can draw, how did I do that? Oh, I see. I have y sub 0, which is the height of this sample. So y sub 0 in this case would be the gap between my two plates. Good so far?
Yep.
Our attempt at three-dimensionality has turned us into something. And so in this place we are doing our stress, which is a force-related measurement, and our strain, which is a deformation. That's delta x there, strain, that's how far things are moving, is done under shear conditions. And shear conditions, like I said earlier, means that this bottom part is not moving while the top part is. And I'm going to try not to scroll down so that you can keep seeing my little picture here. So shear stress, which is different than this stress value up here, but we use the same sigma. And it is equal to force divided by the area over which it is applied. Shear strain, which is labeled as the upside down fish, but without the dot on top of it, because this is just strain, this is not time relational. When we put the dot on top, that means it starts to become time relational, is equal to the deformation, or that strain value, delta x, divided by the height. So shear strain is this value as it relates to this value here. So we're kind of looking at this triangle of information there. Good? And then the one that we've talked about a couple times is shear rate, which is shear strain but time relational. And it is 1 over y0 times dx of t, I'll explain all of this in a second, dt. Effectively, we've got dx and over y0. The only difference is we've brought in, I guess it's this section here, we brought in this time consideration. So I'm gonna just and we have the elastic modulus, which is stress over strain, and that's shear stress over shear strain in a situation like this. And we have viscosity is shear stress over strain rate. And it's worth noting that, again, the math is proving that elasticity, E-L-A-S-T-I-C-I-T-Y, sure. Again, the elasticity is not time dependent. But viscosity is. going just right back to what we were talking about, that the spring deforms immediately. There's no time question, where a dash pot takes time. So it's fun to see that the math, applies. Now, all of this is kind of assuming that I just have like one big square area. The thing that I've drawn here is this nice geometric looking shape. The problem is all of this is happening rotationally.
Which is a whole another game.
It is a whole nother thing. I'm gonna just like really quickly go through it. So the stress, the shear stress, the shear strain, and the shear rate are all calculated. So I can't just like apply a force in a rotational rheometer. In reality, I am applying a torque. Its unit is Newton meter. And this is effectively rotational force. So if we're thinking about like non-rotational, where I'm just sticking my sample in, say, a mechanical tester and I'm pulling on it or pushing on it, we've got a force value. Torque is our rotational force. We also have angular displacement, which is usually measured in degrees or radians. And this is going to be how far a single point moves on the rotational axis. Remembering that in the case of a circle, "90 degrees" is a lot farther on the outside than it is on the inside. So when I'm talking angular displacement in degrees, that is not at all the same as spatial displacement. Up here, I was working with a spatial displacement. I was just measuring the displacement. When I'm working on a rotational instrument, the physical delta x is changing depending on the radius at which it is present.
And if it's in radians, then it's super easy at any point, because you just like, oh yeah, multiply by the radius. So neat.
And then the other one we're measuring is angular velocity. And that is usually going to be degrees per second or radians per second. And this is going to be speed. Again, remembering that speed is going to be different from the outside to the inside. At the outside, we're going to be moving a lot faster than on the inside, as far as like millimeters per second or whatever. But degrees per second is the kind of constant rate. With all of these, I'm going to turn back to my kind of darker blue. These can be converted to shear stress, whose unit is pascals, shear strain, whose unit is degrees per degree, or radians per radian. Unitless, effectively. And I do know that this looks like a percentage. That's not a percentage. That, not percentage. It's degree per degree. Or the shear rate, which is 1 over seconds, or inverse seconds. In order to convert those across, the torque, the angular displacement, and the angular velocity, to convert those across to the stress, strain, and strain rate, you need to know the gap Coming back up here, you need to know the gap and the diameter of the plates. Good? Questions so far?
Nope.
Okay. So far I've been talking about something called a parallel plate, which is where literally my top plate, and my bottom plate are perfectly parallel to one another despite what my drawing capabilities may imply. And we fill our sample in between the two. There's another really common fixture called a cone and plate. I'm gonna scoot that over just a little bit. Where I have, let me draw. We're fine, everything's fine. And I'm drawing it a little bit more exaggerated so that you can tell. Usually this, the cone is like a degree or two. Like it's very, very shallow. And I fill my material in around the cone and the plate. And just to zoom in a little bit on kind of what's happening in the center here. And they don't physically touch one another. They just look like they would. So if I were to continue those lines down, they would touch, but there's a little flat space in the middle. On these, the angle here we call beta. This distance we call y. And then we've got the radius. Oops, that was way too thick. So that's just a little zoom in on the center of the cone and plate. We've got this. It looks like it's touching the way I've drawn it here because it's nearly touching. We just have a tiny little cutout right here to make sure that we're not actually making contact with anything. Am I back at 100? Oop, there we go. So let's talk about sort of the pros and cons of the two geometries, because there are absolutely times when you should use one and not the other. And I'm going to choop. I will label it on this one as well. We've got y is our gap here. And then I've got my radius there. Zooming back to our normal. So gap being the distance between the two plates. For a cone and plate, the gap is automatically set. goodness. And it's as if the tip of the cone was touching the plate. It can't be changed. With a parallel plate, it is adjustable. And the gap size, which is Y, is related to, and I'm going to draw the little like related to symbol there, the shear strain.
Fish on the side, fish upright.
Fish upright, yes. Sideways fish, upright fish, and a Y.
Oh, yeah.
When you are setting this, especially if you've got, sorry, been lots of talking lately. When you are setting this, especially if you have a slurry of any sort, so toothpaste would be an example of that. Toothpaste has tiny little grains inside of it. You want your gap to be 10x to 100x your largest particle size. The reason for that is, can you imagine if I had my gap the same size as my largest particle? Am I going to be measuring the flow of the particles past each other, or am I going to be measuring the grinding of the one particle? More the grinding. And these parallel plates have to be like very, very nice and predictable. Scratches in them really throw off the measurement for some materials. So it's important to make sure that gap is big enough that if 10 of my biggest particles clump together, I'm not going to create a problem for my instrument. I don't want to cause damage. The radius of our geometry, that's the R. Because of these sloped edges of our Conan plate, the strain is constant at all values of R. What that is that when I was talking earlier about how speed changes with respect to R, with a Conan plate, in addition to speed changing, the actual gap changes as well. And those two cancel out. You can do the math yourself. I haven't written it clearly enough that I'm going to go through it. But the math cancels them out to the point where we do have a steady strain at all R positions. And by way of information, the angles, that's that beta value, the angle on a Conan plate, does affect the strain and the strain rate for sensitivity. So there are some considerations about what angles you want to use. For the parallel plate, the problem is the strain is larger at, let me write, higher R, so farther away from the center, at a larger kind of distance from the center. This is more dramatic for small gaps. So the bottom line of all of this is that the Conan plate is best for no particles, so something that isn't a slurry. And it's going to be best for samples whose properties change dramatically with shear strain. So, strain sensitive samples, and for low viscosity samples. So if you have strain sensitive, low viscosity, and no particulates, you're going to want to choose a cone and plate.
Yep. Wrong is that?
Do you have you have yours backwards from what I drew?
Yeah. It's like,
Cool.
huh.
Yeah, so cone and plate is going to be best for non-slurries, strain sensitive, and low viscosity.
And I'm assuming it's the inverse of those for the
Yep.
parallel plate.
So it's going to be best for slurries or anything with particles, stuff that has uniform viscosity, which means it's not strain dependent. And if you need smaller strain fluctuations.
Strain dependent viscosity, like the what would it be? Crap. Like the higher, is it higher strain rate the more viscous, or?
Yes, so if there is something where the faster you move it, the viscosity is going to change. So that'd be shear thinning or shear thickening kind of materials. Then the cone and plate is going to be a better choice for you. So that would be an example of something that is shear dependent. Oh, sorry, I wrote the wrong thing.
So being on fluid scoper for cone and plate.
There are two others, so these are the most common, cone and plate and parallel plate. Those are the two most common fixtures that we're going to use. There are two others that you can use for very low viscosity. Oh wow, that was a really terrible. We can do a concentric cylinder, sometimes also called a cup. And it is very literally a cup.
That's way too big.
And on the inside, we have another cylinder here that rotates. And in this case, we have this gap distance between the internal and the external cylinder. So that effectively becomes our Y, or our gap. And what's nice about this is I have an increased surface area. increased drag, which then increases my sensitivity. Make sense?
Yep.
For very high viscosity samples, we have torsion. This is kind of eking into the elastic properties samples, where I have such high viscosity, it is so resistant to flow that it's probably gonna start like bouncing back a little bit. We're talking like silly putty kind of situation where we're like, this is effectively a solid.
It's rubbery,
Mostly.
but it'll still seep into the carpet.
Yeah, oh my gosh, yes it will. So this is where we're talking like, it has viscosity, but its resistance to flow is so high that it's sort of effectively a solid to us.
Latex. Sure,
Latex, yep, absolutely. With these kind of samples, we clamp them.
Let's go steal the jig
Let
from
me...
the standard material, the universal testing machine.
Yes, we actually have ones that are, a little bit more sensitive than that. Testing instruments for like just mechanical testing are huge. This, we are talking about millimeters, not anything bigger than that.
Not centimeters.
We are on a very, very small scale here. So this is going to use clamping to transfer those rotational forces. With really thick samples, a lot of times a rotational setup like the cone or the parallel, they're just gonna skip across the surface or slide instead of actually transferring those rotational forces. So there is, in this case, usually a need for higher torque. And these samples also usually have higher elasticity. So sometimes you'll just rotate, and sometimes you'll actually do sort of a back and forth oscillation of like back, forth, back, forth, back, forth. That is true actually of all four of these. The torsion attachment, the concentric cylinder, the cone and plate, or the parallel plate, all of them, you can do rotational, where it just spins round and round and round, or you can do oscillation, where you're going back and forth and back and forth.
So the oscillation is interesting because you can tell based on the phase that the bottom sees, like that the force returns because you're going one way and then you're returning.
Yes.
How much it is like a fluid, or how much it is like how much it is like a solid.
Exactly. So actually, we were about to talk about that. Flow versus oscillation, how you choose which properties to use. And oscillation. I know I used green for viscosity, or for elasticity earlier, but there's only as many colors as we have, so we're going to use our orange and our green. So this is orange. It is sort of a reddish orange, but I try not to use red and green together because a very high percentage of scientists are red-green colorblind. So generally in my videos, you will not see me using red and green right next to each other. I try to separate them with some third color, but this is a very reddish orange, so there's only so much I can do. Flow is going to mainly tell us viscosity information. And the reason for that is because this flow is spinning around and around and around. I just have kind of this unidirectional motion. And I really don't give it I don't give the material much of an option to bounce back. We're just moving in a direction. If I rotated and stopped, I would give it an opportunity to maybe bounce back or return. But flow, when it's just like round and round and round and round, we're just mostly seeing viscosity. And we kind of already talked about this, but we're gonna talk about it again. You can create a graph of stress versus strain, essentially viscosity, as it relates to shear. And is that shear rate? I think it is, yeah. So something that has a constant viscosity no matter how fast you're rotating. Do you know what we would call that?
Newtonian.
You've already written that. Look at that.
Yeah. Yippee.
That's going to be something Newtonian. We talked about like honey.
Water.
Water. A lot of oils. Really these like very simple kind of materials. I can also have something whose viscosity decreases as I get faster and faster. What do we call that one?
Shear thinning.
Shear thinning. Can you give me an example of something that is shear thinning?
Lip balm.
Lip balm, yep. Most cosmetics.
Yep.
Ketchup. Because I want it to flow when I squeeze on it. That's a shear when I'm squeezing the bottle and it's coming out at the top. But I don't want it to just like flow off my hot dog or like soak into the bun. So it has to have a little bit of that spring back.
Yep.
Paint also. Because I want it to be smooth when I put it on the wall, but I don't want it to just like off the wall when I'm done. That'd be like really disappointing. And then on the other side, what is something that gets thicker as you go faster?
Oobleck.
Yep. Some mineral slurries. So if you like put mica or other kind of platelet-shaped powders into liquid, black. I think that's how you spell it, black. Is it CK? It might be CK.
I don't know.
I've written CK in my other notes, so we're gonna say that that's how that is.
So, yeah.
With shear thinning and shear thickening, we're gonna do a little asterisk on both of these. There's a property called thixotropy that we can measure. That is where we would do flow and kind of time relation. So you would flow it and then you'd stop flowing it. Do you know what thixotropy is?
I do not remember the specifics, but I remember it being a pain in the rear end.
I'm only going to talk about it as a concept and not as a math problem or physics problem. It's the study of recovery. So after I have shear thinned my ketchup, how long do I have to wait for it to return to its high viscosity state? This is important because if you've ever had like a really crappy ketchup, it's gonna have a really long recovery period. So you like plop it onto your hot dog and then it does soak into the bun because it stays thin, for a long enough time for the bread to like, and you're like, nah, now everything's soggy. Where a good quality ketchup is going to have a faster recovery, where you're gonna plop it onto your hot dog and it's almost immediately going to recover its thicker viscosity. And thixotropy is that value that we're measuring. It's, let me see, do I have it written down? I don't have. But it's essentially like speed of recovery is thixotropy.
Is it like in time, like time
Like
to how much it was
unit?
far? Yeah.
Let's ask the internet. It is the time-dependent shear thinning property, thixotropic. Yeah, this Wikipedia article is like, honey from honeybees may exhibit this property, which Newtonian materials don't have thixotropy because there's nothing to recover.
Mm-hmm.
But it's like very specific. They're like heather honey or manuka honey, which I think that's the most fancy honey that exists, are vaguely shear thinning. Screen being done. It's not talking about any sort of units on this Wikipedia page. So I would imagine it's a relation of like recovery per minute or something along those lines. But it is more a study of recovery than it is like a specific unit. So I'm sure there are units out there that we use. But when we want to study more of like viscoelastic properties, so not just viscosity, I'm actually realizing green is perfect for oscillation because I used green for elastic earlier. What I should probably use is purple because purple was the viscoelastic and oscillation gives us a little bit of both. But anyway, so this is instead of going round and round and round where I rotate a certain amount and then I come back and then I rotate that amount and come back. There are so many variations on oscillation that we can do. We can do frequency ramping, where I travel a set distance and the speed changes. Instead of writing speed, I'm going to write angular. What did I use the word language earlier? Angular velocity. So with a frequency ramp, the angular displacement is the same, but the angular velocity increases. So I would like go from point A to point B and back. And then I go A, B, back, A, B, back, A, B, back, A, B, back. And I'd be like faster and faster, faster. Another option is an amplitude ramp. Where your angular displacement changes, but your angular velocity is constant. So that would be you go forward and back 1 millimeter. And then forward, well, it'd be degrees. Forward and back 1 degree, forward and back 2 degrees, forward and back 3 degrees, forward and back 4 degrees. So you're slowly increasing how far you're traveling. This one, you'll notice that if the velocity is the same and the displacement changes, then my frequency is changing a little bit. You can keep the frequency the same so that the velocity changes also. That's kind of up to you. We also can hold the frequency and the amplitude all the same, and we can do a temperature ramp where the temperature changes. I know that's, very not logical based on the name of it. In all of these, oh, nope, not position. This is time. In all of these, we can draw this graph where the x-axis is time and the y-axis is position. And the instrument is going to do something akin to this. So I've got my home position. It's going to increase, pass home, move backwards, pass home again, move forward, etc. So I'm kind of going back and forth and back and forth. And it's not doing it in a what's called a triangle waveform, so it's not starting at home, going to a position, going back. We do have this change, time versus position, that's a velocity. So I do have this sort of like sinusoidal change. If my material is mostly solid or elastic, then the position of the material with relation to time is going to follow what the instrument is providing. Because we remember that elastic materials don't care about time. They are just immediately responsive. Compare that to a viscous material. And that would be like, I'm 100% viscous. The material itself is going to have a delay. So it's going to not respond for a minute, and then it'll respond. I have not done that. Because we've got that dash pot situation.
If only we had something that went from 0 to 1.
In this situation, my offset, do you remember I talked about tan delta earlier as a sort of ratio between that elastic response and the viscous response? Tan delta here is equal to 90 degrees. So I've got an offset in my sine wave. Where here, my tan delta was nothing. I'm gonna not go through all of that. That's like not worth it. So for a viscoelastic material, then tan delta is somewhere between 0 and 90 degrees. So my material is going to exhibit a little bit of this elastic behavior, a little bit of this viscous behavior, and the offset's going to be maybe here.
And can we write that as a percentage? Because it's 0 to 90.
Yeah, you could
take
write.
Sine of the angle of.
You could write that as a percentage if that's something that you want. Yeah. I think that's as far as we're going to go through rheology. There's quite a bit more to it as far as like the math that goes into G prime, G double prime, all of like these calculations here that we kind of half went through. And there are plenty of videos that go really in depth into the math, and I think the Wikipedia page does a decent job, if I'm remembering properly as well. But yeah, that is as far as we are going to go. From a material standpoint, for our last minute, can you think of reasons, like what causes viscosity from a material scientist standpoint?
I'd say ionic bonds and temporary covalent bonds that are between different parts of the fluid.
Yep, exactly. That could be something that would maybe cause shear thinning, where I kind of have to break some bonds and then it like thins out over time or with speed. Molecular size in a polymer. If I have a really large particle versus a really small particle, you can think of it like spaghetti noodles versus macaroni noodles. Macaroni noodles actually flow pretty well because they're small enough they don't get tangled, where spaghetti noodles sort of like flop. that would be like a higher viscosity because they get all tangled with one another. You can have attractive forces like dipoles, which kind of create a temporary quasi-ionic bond between things. Cross-linking can absolutely change things. With temperature, most things are going to get a little bit thinner because you give the molecules a little bit more energy and they can kind of bounce off of one another.
Do you know of any that get thicker with temperature?
If the material is curing, then it would get thicker with temperature. So there are some
True.
thermoset polymers where it
That
would
do
maybe
that.
get thicker with temperature. Other things would be clumping. I talked about that a little bit with the particles, and that can be clumping on a molecular side or on sort of a more of a macro ceramic particles kind of side of things. Also, friction between different layers can cause a thicker or thinner kind of reaction. So there are all the
Peanut
things.
butter and jelly sandwich.
Peanut butter and jelly sandwich, precisely. We've got a non-homogeneous thing there. That's a lot more to study, but that is the idea. Do you have any other questions about rheology? Thoughts?
Nope.
Awesome.